Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series on applied electronics, and we have been going through a set of lectures on semiconductors, and in this lecture number 7 for the students who are doing physics of materials, the syllabus for the chapter 5 or unit 5 is given here, and we are going through the semiconductors, N type and P type semiconductors rather than intrinsic semiconductors, which we have been seeing in the last lecture. The contents of today's lecture are as follows. We will have a calculation which will be doing on the energy gap of semiconductors, then we will go to extrinsic semiconductors, then the dopants which are being used to make intrinsic semiconductors as extrinsic semiconductors, thereby we will be obtaining what are called N type and P type semiconductors. And finally, the calculation of the donor ionization energy. And let us recapitulate what we have been seeing in the last few lectures, and the area of semiconductors is very important, technologically it is important from the point of view that it is used in very many areas, starting from electronics, optoelectronics, and lasers used in surgical procedures, so medical electronics and so on, and basically these materials which we are talking about are having their conductivities midway between metals and the ceramics or the non-conductors. Metals are very good conductors, insulators are very poor electrical conductors, the semiconductors, the conductivity lies between these two ranges, right. So, and again the intrinsic semiconductors, by this what I mean is pure silicon or pure germanium, they are being studied for gaining a basic understanding of the structure, bonding properties and so on, but from the point of view of application we have to dope them, we have to add certain impurities and make them what are called N type and P type semiconductors. The situation is something like this: no one would like to have pure gold. I have a gold ring. Now, pure gold will not be of very much use, in the sense you have to intentionally add copper to gold. Why do you want to add copper to gold? Because pure gold is not malleable, it cannot be shaped, right, it is not very ductile. So, pure gold is not the one that is being used for ornaments. Similarly, we are sitting in a hall where we have got steel beams. What is steel? It is not pure iron. Pure iron is of very little application. Iron is to be doped or alloyed with carbon, and so also the pure semiconductors are so called intrinsic semiconductors, which we have been dealing with in the last few lectures. The pure semiconductors for which we calculated the number of electrons in the conduction band, number of holes in the valence band, you got an energy gap here, you got a conduction band, valence band. Now, we calculate the intrinsic carrier concentration by evaluating the number of electrons in the conduction band, number of holes in the valence band. Now, these are all from for having a theoretical understanding, but in reality we have to dope them, we have to add certain impurities. Let us now see what impurities ought to be added to make them as extrinsic, so that the extrinsic semiconductors only are used for application point of view. Before that, we will do a simple problem. The problem is following: determine the critical absorption wavelengths in the case of silicon, gallium arsenide, gallium phosphide and zinc sulphide, whose energy gaps are 1.1 electron volt. As you all know, silicon has got an energy gap of 1.1 electron volt, whereas the others are 1.43, 2.26 and 3.6 electron volt respectively. What I am trying to ask you to do is to calculate the critical absorption frequency. In the last lecture, we saw that when light is made to be incident on a crystal, is a semiconducting crystal, and there is a critical frequency for which the energy is absorbed. For other wavelengths, the system, the semiconductor system is fully transparent, there is no light is absorbed. There is a critical frequency for which the entire light is absorbed. What is the meaning of that? The absorption means the covalent bonds in the semiconductor material are broken, or in other words, the electrons are excited from valence band to the conduction band. So, the energy gap can be obtained precisely by knowing the critical frequency. So, the critical frequency that you have got nu c here, right, you have got nu c, the energy of the photon, this photon, the critical wavelength is nu c, the energy of this photon gives the energy gap, the exact energy gap is nothing but that particular frequency is able to excite the electron from valence band to the conduction band. So, the energy gap can be accurately determined by optical absorption method, and so in this problem I am asking you to calculate the critical frequencies, right, the frequencies, that is nu c will be h by lambda c. I ask you to calculate the frequency or the wavelength. The critical absorption wavelengths are to be calculated. Therefore, by substituting simply E g value here, you know the Planck's constant, c is the velocity of light, calculate the lambda c. And also I want you to know, to tell me among the various semiconductors which one will have the absorption wavelength in the visible range, which one will have the in the visible light will be absorbed by which semiconductor. In the following table you find the calculated values, and I have the lambda as this particular thing will turn out to be the critical frequency lambda will be 1.240 divided by E g, the energy gap given in terms of so many electron volts. I gave you in the problem the energy gaps 1.1 electron volt for silicon, 1.42 for gallium arsenide, 2.26 for gallium phosphide and 3.60 for zinc sulphide. By substituting these values in the denominator, you have got a constant here, you can calculate the lambda c, the critical wavelength in terms of micron meters. So, the critical wavelengths, they are the wavelengths which will be absorbed, or which when absorbed by semiconductor, the electrons will be lifted from valence band top to the conduction band bottom. thereby the energy gap will be obtained, or in other words, if the energy gaps are given, the lambda c's, the critical wavelengths can be calculated. The calculated wavelengths are shown here, they are in the micron meter. This is a very simple problem. This method is a very straightforward and very accurate method, and this is the method we should be able to distinguish between direct band gap and indirect band gap semiconductors. What is being done by the engineering students or the science students by determining or by measuring the resistivity as a function of temperature, you draw the resistivity or the conductivity as a function of temperature. From the slope you get the energy gap E g, that is the method that is usually adopted in the laboratory, but that one will not give you the distinction between the direct band gap and indirect band gap. So, what I would like to tell you is, from the conductivity measurement that is being made as a function of temperature, plotting log of sigma I and 1 by temperature as I showed in the previous lectures, that will also give you the energy gap, but you should remember that will not be able to distinguish between the direct band gap and indirect band gap, but whereas this is the method which will give you the distinction between the direct and indirect band gaps. Not only that, it is a very accurate method of determining the energy gap. Let us now pass on to extrinsic semiconductors. What is the difference between intrinsic and extrinsic? Intrinsic semiconductor, as I told you, is a pure semiconductor, a pure silicon or pure germanium or pure gallium arsenide. Now, I am going to dope. By doping, the electrical conductivity can be controlled. What kind of doping that I am going to have, and the amount of doping, those things are very important in making the n type semiconductor, the p type, and then what we are going to do is we are going to combine these two. Then we will get what is called a p-n junction, that is equivalent to a diode. In the vacuum tubes we have the diode and then triode, and therefore, here also we will have a n type and p type. Now, let us see what is an n type semiconductor. N refers to negative, right, p refers to the positive. So, what I am going to do now, I am going to take a pure semiconductor in which I am going to add some impurities. What kind of impurity I am going to add, that we will see in a few moment. The electrical conductivity can be increased by incorporating some foreign atoms in the intrinsic semiconductors, either a pentavalent impurity such as phosphorus or arsenic could be added, or you can add a trivalent impurity like aluminum, gallium, etc. Right. You know what is the valency of silicon? Silicon, germanium, they belong to the fourth group in the periodic table. Fourth group means the valency is 4. The valency of silicon is 4, valency of germanium is 4. They are the pure semiconductors. Now, I am going to add arsenic. Where do you find arsenic? You find here silicon here, arsenic is here or phosphorus is here, right. With the parent material silicon, if I add phosphorus, what will happen? Now, silicon has got a valency 4, as I told you. Phosphorus, whatever the valency is 5. Similarly, arsenic also valency will be 5, right. By adding a phosphorus atom to the silicon crystal, by adding means what? I am replacing one silicon atom by a phosphorus atom, by adding, in the sense by alloying or by adding, or it is the impurity that I am putting now are phosphorus or arsenic. Now, look at the right side of the silicon germanium, namely phosphorus or arsenic. We will come to the left side later. So, by putting phosphorus or arsenic, by putting means I am substituting a phosphorus atom in a place of silicon atom, right. Now, the impurity will be called as a substitutional impurity, right. Now, supposing somebody asks a question to you, you are making a n type semiconductor, where will the atom go? The phosphorus atom will go, or the arsenic will go. Arsenic or phosphorus atoms will go to the sites which are occupied by silicon or germanium. It cannot go, if you got a silicon atom here, Now, the phosphorus being one excess electron, what is the atomic number of phosphorus? 15, 1 electron excess compared to the silicon which has got the atomic number 14. So, the diameters will not be very much different, therefore, the phosphorus that is being added will go to the silicon position, it will not go to a position between the two atoms, right. So, you should remember phosphorus or arsenic which are being added, they are the substitutional impurities, right. I will have a break at this point, then I will come to what are called interstitial impurities. Welcome back after the break. Now, we have been talking about how to make extrinsic semiconductors. We start with a pure semiconductor like silicon which is intrinsic, to which I add a phosphorus atom or arsenic. By adding, what I mean is I am replacing a silicon atom either by a phosphorus atom or a arsenic atom. Now, the diameters which are possessed by phosphorus or arsenic will not be very much different from silicon, and hence they will go to the sites which are occupied by silicon atoms. There are certain atoms like carbon or hydrogen, carbon. Now, these things could be put into the iron or any other metals, they will go to positions in between the two atoms. You have got iron atom here, iron atom here. What is steel? Steel is nothing but iron plus carbon. So, where do you have carbon? Carbon being a very small atom, hydrogen, carbon, their atomic radii very small, they will go to positions which are in between two iron atoms. You have got iron atom here, you are putting carbon which makes you steel. What is steel? Steel is nothing but iron plus carbon. The carbon atom being having is an atom having a smaller radius, it will go to a interstitial site, not a these are the positions occupied by iron. It will not go and replace the iron atom. It is not a carbon, you should remember, it is not a substitution impurity, it is an interstitial impurity. Here the phosphorus and arsenic are the substitution impurities. That is a very important point, that phosphorus atom will go and occupy a position occupied by the silicon atom in the silicon lattice. It will not go and occupy a position in between two silicon atoms. You got a silicon, it will not go and occupy a position in between two silicon atoms, because the diameters are more or less similar. They will go as and occupy positions occupied by silicon or germanium. Okay, that should be understood. Now, talk about the phosphorus atom. What is the valency of phosphorus? It is 5. The bonding requires only 4 electrons. What is the bonding in silicon or germanium? They are fully covalent. All of us know by now the bonding in silicon or germanium are covalent, fully covalent, there is no ionic character. The bonding requires only 4 valence electrons. You have got 1 electron here and you have got 4 valence electrons. Okay. Now, what you do is you are adding a pentavalent or a 5 valence system, right, because the valency of phosphorus is 5 or arsenic is 5. Then the question arises, what will happen to the 5th valence electron? The bonding requirement is only 4. We require only 4 electrons for bonding in silicon or germanium, but now we are putting a atom which has got 5 valence electrons, and now we are worried about the 5th valence electron. What will happen to the 5th valence electron? Similarly, if you are putting a trivalent impurity like aluminum or gallium, a deficiency of electron, it is a 3 valence system, it is a 4 valence system, the 4 electrons are there. Here you are putting you are replacing silicon by aluminum, that means a 3 valence system, a hole is introduced. By this, by adding phosphorus or replacing silicon by phosphorus, you are adding 1 excess electron. By adding aluminum, you are adding a hole, because there is a deficiency electron. They are putting, you have got a 3 valence system, right. There is a deficiency electron number, or in other words, you are adding a hole but now by adding phosphorus you are adding one excess electron. That is the reason excess electron is what is charge of the electron, it is a negatively charged particle. So, by adding phosphorus you are adding excess electrons to the system, that is the reason why they are called n type semiconductors. Okay. By giving a small energy, the fifth valence electron can be removed from the atom, right. That the calculation and the proper understanding will come soon, and the atomic radii of the dopants, if they are nearly the same, as I told you, they will go and occupy the substitution sites. Okay. If on the other hand, as I told you just now, if you are putting hydrogen or carbon in some of the metals, then those atoms will go and occupy interstitial sites, the position or the space available between the atoms, they are called the interstitial sites. Now, whereas this particular thing should be remembered, those who are studying semiconductor physics or semiconductor engineering, you should understand that the impurity atoms will go and occupy substitution sites, or in other words, one may ask what will happen in the impurity, is it a substitution impurity or a interstitial impurity. You will be able to tell that what you are doing is we are adding a substitution impurity, not a interstitial impurity. You are phosphorus or arsenic or aluminum or gallium, trivalent aluminum or gallium, they are the substitution impurities, right. That point should be remembered. Okay. The process of doping by adding a pentavalent atom or a trivalent atom will lead to n type or p type semiconductors. N is mean negative. By adding a pentavalent atom, you are adding a 5 valence system, one excess electron will be there. The bonding requires only 4, but you have got 5 electrons. P type means you are adding aluminum, a 3 valence system. On the other hand, bonding requires 4 valence electrons, you have got only 3. So, a hole is introduced. Okay. A hole means a hole acts like a positive charged particle, and therefore, they are called p type semiconductor. In reality, they are not positively charged particle. One should not confuse hole with the positron. Positron is a real particle, anti-electron is positron, that is the real particle. Here it is only conceptually a p type semiconductor is one in which holes are present. The former refers to the fact that the majority carriers are electrons, whereas in the second case it will lead to the holes will be the majority carriers. In the former, the electrons will be majority carriers. These things we will see later in detail. In the case of intrinsic semiconductors, the number of electrons in the conduction band and the number of holes left in the valence band, they will be equal, that is what I told in the previous lectures. But in this case what will happen is the energy levels of the electrons or holes due to the impurity atoms that we are adding now, those energies can be calculated by using a simple Bohr atom model. It is an ingenious idea given by the Nobel laureate Hans Bethe. So, Bethe gave a very nice idea that the pentavalent, the 5 valence electron will be revolving around the nucleus like an electron revolving around the proton in the hydrogen atom, which was conceived by Niels Bohr. A complicated problem can be simplified to the Bohr atom model, provided you make certain changes in the Bohr's expression. Suitable modifications are to be made as discussed now. If silicon is assumed as the host crystal, the phosphorus of the pentavalent impurity atom, the 5th valence electron of the impurity atom, which is not required for the covalent bonding, becomes a loosely bound electron, but this electron you should remember is not revolving, is not in vacuum, right. It is the entire thing, the parent crystal is silicon, right, that should be remembered, right. This is what you are trying to do, you are adding a pentavalent impurity atom phosphorus to the tetravalent silicon, the 4 valence system, the 5 valence system is being added. Now, we want to know what happens with the electron, right. The 5th electron, now there will be 15 protons, the atomic number of phosphorus 15, right. That means, in a phosphorus atom that you are keeping in a place of silicon, there will be 15 protons and 15 electrons. The bonding requires only 4 electrons, 10 plus 4, 14 electrons, right, 3s2 p2. Only the 4 electrons, the p3, the electron, the third electron, the p shell is not required for covalent bonding, and so it is a loosely bound electron. As I will show you now, the system should be looked upon like this. The phosphorus atom should be conceived as a 15 proton and 14 electron system, right. The 15th electron is a loosely bound electron, right. So, the 15 proton plus 14 electrons will become a positive charge, right, 15 protons and 14 electrons. 14 electrons are required for bonding. Okay. So, it looks like one proton, and the loosely bound electron, the 15th electron is a loosely bound electron. The lone loosely bound electron will revolve around the positive charge. This is the diagram shown here, right. So, the 15th electron is a revolving. Now, what I am doing is I replace, you got a silicon crystal, I replaced one silicon by arsenic. What about arsenic? It is a 5 valence system. The bonding requires, if you look at the silicon, that will be 1 electron here, 1 electron here, 1 electron here, it is a tetravalent system, right. There will be 4 valence electrons which are shared by the adjacent silicon atoms. For the arsenic atom, the valence is 5, only 4 are required for bonding, right. 1 electron will be here, 1 electron will be here, 1 here, 1 here. The 5th electron is a loosely bound electron. It will now try to revolve around the center. What is center? The center, the dark dot now refers to 15 protons and what? How many electrons? 14 electrons, right. The arsenic atom has got 15 protons and 15 electrons, but the bonding requires only 14 electrons. So, there will be 14 electrons and 15 protons, that means 1 excess proton. So, this looks like a positive ion, right. It looks like a proton in the hydrogen atom. So, you got a proton here, a positive charge here, is that understood? Positive charge, and the 5th electron is a loosely bound electron. It will revolve in a big circular orbit, not like orbit in hydrogen atom. In hydrogen atom, you got a proton here, the electron should be revolving like this, right. But here this electron is a very weakly bounded electron. It will revolve in a big circular orbit which encompasses several lattice constants. You got a arsenic atom here, you got silicon here, another silicon here, and so on. So, it revolves in a big circular orbit. From the calculation which I will show now, you will understand the bonding is very weak. It is not like in the hydrogen atom, the bonding is 13.6 electron volt. Here it will be very small. So, this is a modified Bohr model to calculate the bonding energy of the extra valence electron of the pentavalent impurity atom revolving around the single positive arsenic ion. The detailed calculation can be done by making certain assumptions, namely the entire thing is taking place in a silicon lattice whose dielectric constant should be taken into account. Then again the electron is moving in a periodic potential. These two factors are to be taken into account. We will do the calculations in the lecture to come. Now, we will pass on to the summary part of the lecture. The optical method of finding the energy gap is a more accurate method, and it is the method which will be able to distinguish between direct and indirect band gaps. Pentavalent impurities lead to an n type semiconductors, that is adding pentavalent impurities will give rise to n type semiconductor. On the other hand, adding or substituting trivalent impurities in a place of silicon will give rise to p type semiconductors. The donor ionization energy can be calculated using the Bohr atom model, but you should remember certain suitable modifications are to be done. The modifications which are to be done to calculate the donor ionization energy will be discussed in the lecture to come. We will now pass on to the question session. The questions are: what is an extrinsic semiconductor? What are the dopants which are added to make N type or P type semiconductors? How will you calculate the donor ionization energy? With this, we come to the end of the lecture number 7. The rest of the things we will see in the lectures to come. Thank you.